Okay, so now you have appreciated first principles. We are going to look at a section on how to find new techniques to differentiate. How would you normally differentiate this function here? Well, from higher, what you would normally do is expand the brackets, which go quite nicely, and then differentiate. That's exactly what I would do for that. It's quite a straightforward question, but we're going to use it later to show you how our new rule works. This is easy enough, but you will be presented with a lot of complicated functions, so how can we work out those? So how would you differentiate this? You still have the skills that you can differentiate this, but we're going to look at what you would have to do just now from higher to cope with this. So the first thing you would do is you would have to expand x plus 3 squared and change x, root x, to x to the half. When you expand that, you have to multiply everything by x to the half, and remember that x squared is the same as, to the power of 2 is the same as 4 halves, so you end up with 5 halves. So just be careful when you expand your indices. I know you know how to do that. I'm just reminding you that it's tricky. Right, so to differentiate, it will be 5 over 2, and then if you take 2 halves off, you get 3 over 2 and so forth. Just be careful. Remember, when you take 1 off of that, you get minus a half. Yes, I could have wrote that as 9 there. I'm just reminding you that they would all be over 2 to start with, so you could pull out a common factor of a half if you wanted to. I'm going to finish this off by writing it as a third, so that'll be 5 over 2, and remember that means x, the cube stays beside it as the root. This can be wrote as 9, and then I can bring that downstairs to write it as a third. That is fine for where you want to stop, but for me to show you the connection with this in your new rule, I need to express it as a single fraction. So you have 2 root x there, you have no denominator, and you've got a 2, so I'm going to make them all have a common factor of 2 x, a common denominator rather, of 2 root x. What do I do to do that? I need to multiply the middle term by 2 root x top and bottom. So when I multiply the 9 by 2, it gets 18, and I've got the root x there. This one already has a 2, so I just need to multiply it by root x. So normally you can stop there, but we're going to try to get this to be a single fraction. So now I've got a common denominator of 2 root x. Look at this, root x times root x is x, that's fine. But what about this? X times x cubed is x to the 4. The square root of x to the 4, x squared times x squared is x squared. That's not as finished. As well as that, you can factorise that. So 5x squared goes to 5x and x, and the 9 goes to 3 and 3, and you get a lovely answer. Do not stress about what you're doing there, okay? I am just showing you how your original function here will come to this as an answer, to show you that you don't have to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 lines of working to get to this answer, because there's more sophisticated techniques that you can use now, okay? So it's obviously tedious, and in advanced higher maths you're going to be more sophisticated and learn new different rules. So let's have a look at these. Right, in this section, what are you going to do? You're going to learn how to differentiate using something called the product rule. And you might know this word, but a lot of people forget it from earlier on. Product means multiply. So it means multiple functions. Quotient is you get a quotient and a remainder when you divide. Quotient rule means when you have functions that are dividing. And then we're going to look at your exponential and log functions and introduce you to some new functions as well. You don't have to prove these rules, you simply have to learn how to use them. So I haven't went to the effort of showing you the proofs of these. They are actually in your Scholar Unit 1 PDF in the Maths folder, in the Materials folder, but you can also find links online. I have put up attachment at the bottom of all the PDFs that you open up, and it has got links to different videos I've found in YouTube before I can manage to upload my own, okay? But the proofs you can find on here, okay? The product rule can be written as u dash v plus ub dashed, or f dash g plus f g dashed, or a, b, p, q, r, s. It doesn't matter, it's the same idea. So it means the derivative of the first one multiplied by the second function, and then the first function multiplied by the derivative of the second function. It doesn't matter the letters you use, the notation you use, it does the same thing. It depends on your teacher which letters you use, but it's the same rule regardless, and the online Scholar textbook shall be tending to use U and V, and this also prevents confusion if you're initially given f of x as the function in the first place. So that is why I use U and V. So if you look at any of the past paper answers or any of the notes or anything to do with Mrs. Newlands, you'll find it's U and V. Okay. Right, so let's look at, instead of expanding the brackets, using it this way. That is the higher way, that's what you would normally do. We're now going to try and use the product rule. So that means when I'm talking about the U and the V, the first term is called U and the second term is called V. Product is because they're multiplying. So you can put a U and a V above them if you want, but what I tend to do is put a little box at the side. So you have U dash and V dash 2 times, so I always put one of these boxes at the side, which you'll see in the next, but it's really handy to have it in this way. So in this case here, the U is x minus 2 and the V is x plus 3. So I put that, and the derivative of U is just 1 because you have x there, the minus 2 just disappears, and the derivative there. So that's it. So let's go and do the question. So you have identified the first one is U, the second one is V, and what you'll find is if the rule is U dash V plus UV dash, you get a nice diagonal relationship going on. So if you set it up like that and you go to use the rule, then you'll see that the U dash V part is this diagonal here, and the UV dash is this diagonal. So if you have it at the side, you can see what you're multiplying really easy. If you have them all in a row, then you don't see what's happening. It's this setup here that will make it so much easier for you and for a rule you're going to learn after this. Right, so this is our rule, we know the U and V, we have our information, so let's just use it. So what I normally do is look at what the actual function's been represented with. If it's y, I'll use dy by dx. If it's f of x, I'll use f dashed. So I just write the rule, okay? Then I go U dash V is 1 times x plus 3, and UV dashed is 1 times x minus 2. It doesn't matter which one you put at the front. And in fact, if you've got 1 times, you don't even need the 1 there. Okay, I'm just showing you how it works. Then collect them together, so you'll get 2x plus 1. Okay, that is exactly the same answer as before. You might think, do you know what, that was more hassle than how I would do it at higher. But the reality is you're not going to have nice, fancy, straightforward functions. Right? You're going to have ones with cubes or roots or trig involved in it. Okay. So let's go back to this one then, because this one had 10 lines of working and it was root x and a squared. So you can see this one is more complicated. So what would your U and your V be? The first one would be U and the second one would be V. So then let's consider when you have it as a root, change it to an index before you do it. So let's think about what they would be. And the trick for you, so you can call it a trick if you want, is put it back into root form before you actually do the full differentiation. So if you have U as root x, then I would write that as x to the half to begin with. What is that differentiated? That is a half x to the minus a half, and put it back into root form before you substitute in. It's easier to deal with this in root form, so bring it downstairs and it's the square root. Okay. Next, 2 comes to the front to the power of 1, and there is nothing out of the chain rule. 1 comes out, so you don't have to worry about that. But quite often you'll have a chain rule. Okay, let's go through it. So U dash V plus UV dash, you do cross multiply. So it's 1 over 2 root x times that x plus 3. And then 2 root x times the... Now you'll see here, I've put the 2 to the front, so I wouldn't write root x2, so I'm writing 2 root x times x plus 3. I want them all to be in one nice fraction. So I'm next going to find a common denominator. So I have 2 root x there, so I'm going to have to multiply this top and bottom by 2 root x, okay? So you need to express it as a single fraction. The next thing is then 2 times 2 is 4, and root x times root x is x, so it's actually quite nice. So you get a 4x there. Okay, let's open it. There's two choices at this point. You can either expand it all and collect it all together and then factorise, but I'm going to do something to make you start thinking about how to look at this in a different way. Can you see you've got an x plus 3 there and you've got an x plus 3 squared? You could pull out a full bracket of x plus 3, okay? So there is an x plus 3 as a common factor. If you don't see that, just expand the whole line and then pull it out. But what if you've got an x plus 3 to the power of 4? You don't want to expand that, okay? So x plus 3 can come out to the front. You have one extra x plus 3 there, so I have an x plus 3 in the bracket. And then you've pulled out the x plus 3, so you get 4x. And then you get x and 4x is 5x. And then you get the same answer. I've just copied that over from the first one to show you it's exactly the same answer as before. And it's only done through 1, 2, 3, 4, 5 lines. Okay, so a lot less hassle. Okay. It can actually have three parts to it. So you can have a U, a V, and a W. So if you know that that is, you remembered it was U dash V, so it's U dash V W, and then the V dashed with the U and the W, and the W dash with the U and the V. So it's just whatever you have, you will have the first one differentiated with the others combined. So you'll have U dash V, W, UV dash W, UV, W dash. So the derivative of the first one, then the derivative of the second one, then the derivative of the third. So this time we've got UV and W, so U will go to 3x squared. Be careful about this one. The 4 will come to the front, it will be to the power of 3, but the chain rule comes out with 2x as well. So bring that to the front and have it as 8x. And then sine 7x will go to 7 cos 7x. Right, let's substitute in. I've not done any animations here. I've got the derivative with these two. Then I have the derivative of v dashed with these two. And then I have the derivative, but I've used the colour there to show you. I've brought that 7 right to the front. So it's the 7 cos 7x, but I've just put it all like that with these two. Do you notice you've got an x squared minus 5 to the 4, an x squared minus 5 to the 3, an x squared minus 5 to the 4? That means you could pull out an x squared minus 5 to the 3 because they all possess that. That has sine 7x, cos 7x, so you cannot pull that out because they are not the same. But you've got an x squared, an x to the 4, and an x cubed, so you could pull out x squared. You can't pull out a number there because that's got a 3, an 8, and a 7. So you can pull out x squared. They've all got in common an x squared minus 5 to the 3. That leaves you with a 3 and one extra bracket of that with the sine x. That x squared would leave you with an x squared coming out here, but you've pulled out the full bracket. So I'm just showing you that as much as you would think that you can do something else with that, you could maybe make it a bracket in a bracket and get a common factor of sine 7x there, but actually it's only the ball only got x squared, the ball only got to the power of 3, the most you can pull out. Okay, so your temptation is to keep going, but just stop. Right, what have you got to do? So now you're going to try two tasks for me. I've managed to have some questions from a Maths in Action textbook. I don't have one with me, so this is from just past smart notebooks that I have this, and then following on by some questions from exercise 8 and Scholar. Both sets of questions are on here and they're in the PDF, so you can just use the PDF to look at the questions, and after that you can check your answers. Okay. This is the first questions from Maths in Action, just to let you know, and then the next ones you can find in Scholar. Care with 27 onwards because they're a bit trickier. So you'll see you've got 20 to 27. 27 has 3 elements in it, and then can you remember about equations of tangents and stationary points, because you had tasks to remind you about that the other day. You'll find that your answers to these will be on the PDF, so you can just work through those if you don't want to hear my voice. However, the solutions to exercise 8 are not in the PDF except for a couple of handwritten ones. They are, you can find the exercise on page 61, 62, but you can find the answers on page 247 when you scroll down. The solutions to the first set of questions are in this PDF. I'll just quickly show you that then it goes to answers and then you've got the answers. However, I'm not going to go through all of those. They're just handwritten there for you to check. Okay, but these are your first set of questions. So just to remind you, you're going to have a set of questions that are on the next slide, and then you can either use this slide to do the PDF to do the exercise 8, or you can go to the PDF and just use them without having to be on a video. Okay, right, enjoy.